Hello and welcome to part 4 of this e-module on HVAC systems. This is the last of the 4-module series on HVAC systems, where we will learn about the other types of air conditioning systems, namely fan coil unit, that is FCU, packaged units, variable refrigerant flow, that is VRF, precision air conditioning, that is PAC, and chilled beams. Apart from these, we will also learn in brief about the thermal energy storage system that is used for air conditioning. Let's take a look at the learning objectives of this module. By the end of this module, you will be able to describe the fan coil unit FCU, classify types of FCU and working principle of it, understand original equipment manufacturers OEMs, explain what are package units, discuss the types of package units and maintenance checks. Describe the types and working principle of VRF system. Explain maintenance protocol and troubleshooting. Describe what is PAC, components and classification and working of PAC. Discuss types and benefits of chilled beams. Understand what is thermal energy storage. In the previous 3 modules of HVAC, we covered central air conditioning, heating and ventilation main topics and equipment. In this module, we will cover all other units that are also very helpful and efficient in conditioning the air and that can be used in various combinations in a facility or office building according to the basic needs, space and requirements and therefore cannot be overlooked. Let us begin with fan coil units, FCUs, and see why are they so important to us. A fan coil unit or FCU is one of the most versatile way of providing conditioned air into a served area. FCU has multiple benefits like it has a small footprint, it has great controllability, it can be used with a variety of grills and diffusers. It allows the conditioned air to spread around served room via discharge ducts. A single unit of FCU can distribute air to larger area. It has been used for many years now to provide local heating and cooling. So, what do we mean by fan coil unit? Let's take a look. A fan coil unit FCU is a simple device consisting of a heating or cooling coil and fan. It is part of an HVAC system found in residential, commercial and industrial buildings. Typically, a fan coil unit is not connected to ductwork and is used to control the temperature in the space where it is installed. It is controlled either by a manual on or off switch or by thermostat. Fan coil units can be wall mounted, freestanding or ceiling mounted and may be concealed in ceiling voids. The FCU has inherent advantages and are prescribed for certain areas because the use of fan coil unit is an important step of saving energy in air conditioning. It allows individual and flexible air conditioning in limited areas at low installation, operating and maintenance costs. Fan coil units are divided into 2 types. 2-pipe fan coil units. 2-pipe fan coil units have one supply and one return pipe. The pipe supplies cold or hot water to the unit. This requires system changeover from heating to cooling or cooling to heating. 4-pipe fan coil units. 4-pipe fan coil units have 2 supply pipes and 2 return pipes. This allows either hot or cold water to enter the unit at any given time. Since it is often necessary to heat and cool different areas of a building at the same time, due to differences in internal heat loss or heat gains, the 4-pipe fan coil unit is most commonly used. Let us now look at the components of an FCU. FCU is made up of 5 main components: fan, fan motor, filters, heat exchanger, condensate drain tray. Now we will study each component in detail. Let's start with fans. Depending on the size of the fan coil units, 2 or 3 dynamic balanced rotary blowers with double-sided suction and impellers with forward bent blades are fitted. The fan can be with a bucket wheel and a plastic spiral housing or with an aluminium bucket wheel and zinc plate spiral housing. The fans are selected such that the required static pressures can be achieved at low sound power levels. The fan can be operated at 6 speeds via a step transformer, 3 speeds of which have been preset. The fan, which is provided with self-lubricating bearings, is maintenance-free. Next component is fan motor. Permanent split capacitor motor PSC and shaded pole SP motors are used. 2-speed high-low switches or 3-speed high-medium-low switches to vary the fan speed and a thermal overload protection is provided. Typically, this speed selector switch is integral to the room thermostat and is set manually or is controlled automatically by the digital room thermostat. Next is heat exchanger. The cooling only or cooling and heating registers are made of copper pipes and aluminium blades. The 3-pipe row register consists of a cooling register with 2 tube connections. The 4-pipe row register consists of a 3-pipe row cooling and 1-pipe row heating register, each with 2 tube connections. The length of the register depends upon the required performance. The connections are attached on the left or right hand side. Each register is fitted with valves for venting and draining. Now we will study about FCU filters. Filter unit consists of a steel frame and a renewable filter medium. The filter is readily accessible from either the rear or underneath the unit. Depending on its degree of soiling, the filter must be cleaned or changed at least twice a year, since a soiled filter will increase the pressure loss. The last component is condensate drain tray. An insulated condensate drain tray collects the water of condensation. It can be connected to the drain channel. The connecting line for the water of condensation must have a 3 to 5% slope towards the drain. Now we will study the working of FCU. A fan coil unit FCU receives chilled water from a chiller line or hot water from a boiler. Water circulates that through the heat exchanger. The fan draws the room air and also some amount of fresh air in a space or plenum in the unit. Then blows the mixed air over the cooling or heating coil in the heat exchanger. The air comes out of the FCU either cooler or hotter than before. In some FCUs, an optional electric heating element may be provided instead of hot water pipes. Now that you're aware about the working of FCU, we will have a look at its uses. FCUs are used in some office buildings and shopping centers and typically recommended where there are multiple small spaces requiring individual control. FCUs are, however, most commonly used as a supplement to a building for which other HVAC systems provide the majority of the air conditioning. Top 5 manufacturers of FCUs are ETA, Blue Star, York, Carrier, Train. Let us study the preventive measures to be followed while using FCU. Check for unusual noise or vibration. Lubricate shaft and motor bearings. Replace air filters. Check all portions of the unit through which air flow. Let's now take a look at work method checklist. Check unit for noise and vibration. Clean and wash permanent filters. Drain and clean condensate pans. Lubricate fan shaft bearings if not sealed. Lubricate motor bearings sparingly using SAE 10-watt motor oil if not sealed. Clean coils by vacuuming, brushing or with coil cleaner. Use fin combs to straighten coil fins. Clean strainer ahead of unit. Now, we will study the maintenance protocol to be followed when using FCU. Blower maintenance. The type of fan operation is determined by the control components and their method of wiring and may vary from unit to unit. Lubricate. Motors equipped with oiler tubes may be lubricated with a 20-weight non-detergent oil. The frequency of the lubrication is dependent upon the operating conditions of the motor. Units subject to frequent fan cycling or those that operate in a dirty environment require more attention than those subject to less severe operation. Motors should be lubricated at least once per year. Some motor designs don't require field lubrication. Possible replacement. Should the motor or blower assembly require more extensive service than simply lubrication? The assembly may be removed from the unit to facilitate such operations as motor or blower wheel or housing replacement. Dust control. Don't allow dirt and dust to accumulate on the blower wheel or housing. This can result in an unbalanced blower wheel condition that can damage a blower wheel or motor. The wheel and housing may be cleaned periodically using a vacuum cleaner and brush, taking care not to dislodge the factory balancing weights on the blower wheel blades. Watch voltage. When replacing motors, be sure to verify that the motor voltage, phase, and horsepower are correct for the unit being installed. Leave bearings alone. The blower shaft bearings are usually permanently sealed and lubricated ball bearings, and no attempt should be made to disassemble or lubricate these bearings. As with a direct drive motor, dirt and dust shouldn't be allowed to accumulate on the blower wheel or housing. Coil maintenance. Coils in most fan coil units can be cleaned by removing the motor or blower assemblies and brushing the entire air face between fins with a stiff brush. Brushing should be followed by a thorough vacuuming. If a compressed air source is available, the coil may also be cleaned by blowing air through the coil fins from the existing air face. Keep in mind that units with the proper type of air filters replaced regularly will require less frequent coil cleaning. We know the uses and maintenance FCU, but have you wondered what happens if you face failure of FCU? Since FCUs are generally used for small enclosed spaces or areas where it is not feasible to take the central air conditioning, there is no alternate means of cooling and a failure may result in loss of air conditioning in that space. Ideally, multiple units in the conditioned space will prevent total loss of air conditioning. You have studied the impact of FCU failure. We will now study top issues that you may face while working with FCU and how to troubleshoot them. Unit not starting. Turn the unit off if it fails to come on when you activate the switch. Open the unit cover and check the fuse. Pull it out and hold it against a white or lit background to make sure it is not blown. Replace it if it is blown. Check the power plug. Make sure it is completely pushed into the outlet. Unplug the unit and inspect the plug for damage. Use a current detector or probe to confirm there is power to the outlet. Look at the delay timer to verify that it is set correctly if all power checks are good. Low chilled water pressure. The chilled water in the cooling coil heat exchanger is what removes the heat and humidity from the air. If the chiller is off or the inlet valve to FCU is closed or chilled water pressure is low, the FCU will not cool the air effectively. Frozen evaporator coils. Your air conditioner's evaporator coil is filled with refrigerant and is responsible for absorbing the heat from the air is like a sponge. Those coils need warm air circulating around them to work properly. When something goes wrong with the airflow and the evaporator coil gets too cold, a layer of ice can build up on the outside. When that happens, you'll get warm air or none at all coming from your air conditioning supply registers. Low airflow. The fan may not be working properly due to a faulty motor, lack of lubrication. If the fan is working, check the condition of the filter. Clean or replace as required. Thermostat faulty. Especially if you still have the old dial-type thermostats, they could be incorrectly calibrated, which means the FCU isn't getting the right instructions from the control system. This problem is fairly easy to fix by replacing or recalibrating the thermostats. Clogged drains. All the moisture that the FCU removes from the air has to go somewhere. It's supposed to be removed from the space through a drain line, into a pan, finally down a drain. If the line or drain gets clogged or the pan gets full, the water can back up and damage your system. You can also wind up with water leaks that damage your walls, ceilings and furnishings. If you don't see it right away, you'll eventually have mold growth. Let us now understand what are package units. The window and split air conditioners are usually used for the small air conditioning capacities up to 5 tons. The central air conditioning systems are used for where the cooling loads extend beyond 20 tons. The packaged air conditioners are used for the cooling capacities in between these two extremes. The packaged air conditioners are available in the fixed rated capacities of 3, 5, 7, 10 and 15 tons. These units are used commonly in places like big enough to preclude use of split ACs and small or located away from central areas to justify the extensive ductwork and piping required for a central AC. As the name implies, in the packaged air conditioners, all the important components of the air conditioners are enclosed in a single casing like window AC. Thus, the compressor, cooling coil, air handling unit and the air filter are all housed in a single casing and assembled at the factory location. The packaged ACs can be ductable or without ducts. Depending on the type of the cooling system used in these systems, the packaged air conditioners are divided into two types, ones with water-cooled condenser and the ones with air-cooled condensers. Now that you have understood what package units are, let us understand their types. We will begin with packaged air conditioners with water-cooled condenser. In these packaged air conditions, the condenser is cooled by the water. The condenser is of shell and tube type with refrigerant flowing along the tube side and the cooling water flowing along the shell side. The water has to be supplied continuously in these systems to maintain functioning of the air conditioning system. The shell and tube type of condenser is compact in shape and it is enclosed in a single casing along with the compressor, expansion valve and the air handling unit, including the cooling coil of the evaporator. This whole packaged air conditioning unit externally looks like a box with the control panel located externally. In the packaged units with the water-cooled condenser, the compressor is located at the bottom along with the condenser. Above these components, the evaporator or the cooling coil is located. The air handling unit comprising of the centrifugal blower and the air filter is located above the cooling coil. The centrifugal blower has the capacity to handle large volume of air required for cooling a number of rooms. From the top of the package air conditioners, the duct comes out that extends to the various rooms that are to be cooled. Now we will look at the second type of package unit, that is, packaged air conditioners with air-cooled condensers. In this packaged air conditioners, the condenser of the refrigeration system is cooled by the atmospheric air. There is an outdoor unit that comprises of the important components like the compressor, condenser, and in some cases, the expansion valve. The outdoor unit can be kept on the terrace or any other open place where the free flow of the atmospheric air is available. The fan located inside this unit sucks the outside air and blows it over the condenser coil, cooling it in the process. The condenser coil is made up of several turns of the copper tubing and it is finned externally. The packaged ACs with the air-cooled condensers are used more commonly than the ones with water-cooled condensers. Since air is freely available, it is difficult to maintain continuous flow of the water. Let us understand its structure. The The condenser coil is made up of several turns of the copper tubing and it is finned externally. The cooling unit comprises of the expansion valve, evaporator, the air handling blower and the filter are located on the floor or hanged to the ceiling. The ducts coming from the cooling unit are connected to the various rooms that are to be cooled. Now that you have understood about the types of package units, let us understand their maintenance checks. Daily maintenance checks. Clean or change your filters once a month or as needed. Maintain the system according to your train manual. Clean outdoor coils whenever they appear dirty. Remove foliage and clutter from around the outdoor unit. Clean the supply and return registers in your home and straighten their fins if bent. Annual maintenance checks. Ducts, filters, blower and outdoor coil for dirt and other obstructions. Duct leakage. Adequate airflow. Correct refrigerant charge. Refrigerant leaks. Electric terminals and if necessary, clean and tighten connections and apply non-conductive coating. Lubricate motors and inspect belts for tightness and wear. Correct electric control, making sure that heating is logged out when the thermostat calls for cooling and vice versa. Correct thermostat operation. Let's now look at what variable refrigerant flow (VRF) systems are. The term VRF or variable refrigerant flow refers to the ability of the system to control the amount of refrigerant flowing to each of the evaporators, enabling the use of many evaporators of differing capacities and configurations, individualized comfort control, simultaneous heating and cooling in different zones, and heat recovery from one zone to another. VRF systems operate on the direct expansion, that is DX principle, meaning that heat is transferred to or from the space directly by circulating refrigerant to evaporators located near or within the conditioned space. Refrigerant flow control is the key to many advantages as well as the major technical challenge of VRF systems. Note, the term VRF systems should not be confused with the centralized VAV, that is variable air volume systems, which work by varying the airflow to the conditioned space based on variation in room loads. Variable refrigerant flow or VRF systems are similar to the multi-split systems which connect one outdoor section to several evaporators. However, multi-split systems turn off or on completely in response to one master controller, whereas VRF systems continually adjust the flow of refrigerant to each indoor evaporator. The control is achieved by continually varying the flow of refrigerant through a pulse modulating valve, that is PMV, whose opening is determined by the microprocessor receiving information from the thermostat sensors in each indoor unit. The indoor units are linked by a control wire to the outdoor unit, which responds to the demand from the indoor units by varying its compressor speed to match the total cooling and or heating requirements. VRF systems promise a more energy efficient strategy. Estimates range from 11% to 17% less energy compared to conventional units at a somewhat higher cost. The modern VRF technology uses an inverter-driven scroll compressor and permits as many as 48 or more indoor units to operate from one outdoor unit. Varies from manufacturer to manufacturer. The inverter scroll compressors are capable of changing the speed to follow the variations in the total cooling or heating load as determined by the suction gas pressure measured on the condensing unit. The capacity control range can be as low as 6% to 100%. Refrigerant piping runs of more than 200 feet are possible, and outdoor units are available in sizes up to 240,000 BTUH. VRF systems are engineered systems and use complex refrigerant and oil control circuitry. The refrigerant pipework uses a number of separation tubes and or headers. Refer schematic figure above. A separation tube has two branches, whereas a header may have more than two branches. Either of the separation tube or header or both can be used for branches. However, the separation tube is never provided after the header because of balancing issues. Now we will study the types of VRF system. VRV or VRF systems can be used for cooling only, heat pumping or heat recovery. On heat pump models, there are two basic types of VRF system: heat pump systems and energy recovery. Let us have a look at VRF heat pump system first. VRF heat pump systems permit heating or cooling in all of the indoor units but not simultaneous heating and cooling. When the indoor units are in the cooling mode, they act as evaporators. When they are in the heating mode, they act as condensers. These VRF heat pump systems are effectively applied in open plan areas, retail stores, cellular offices, and any other area that require cooling or heating during the same operational periods. Next, let us look at heat recovery VRF system. Variable refrigerant flow systems with heat recovery, that is VRF HR capability, can operate simultaneously in heating or cooling mode, enabling heat to be used rather than rejected as it would be in traditional heat pump systems. VRF HR systems are equipped with enhanced features like inverter drives, pulse modulating electronic expansion valves, and distributed controls that allow system to operate in net heating or net cooling mode as demanded by the space. VRF HR mixed mode operation leads to energy savings as both ends of the thermodynamic cycle are delivering useful heat exchange. If a system has a cooling COP, that is coefficient of performance of 3, and a heating COP of 4, then heat recovery operation could yield a COP as high as 7. Now we will have a look at maintenance protocol of VRF system. Indoor. Check unit status. Check the availability of power. Check blower for any abnormal noise or vibration. Ensure drain is not clogged. Check the BMS connection. Check for the unit sequencing and scheduling. Check the filters are clean. Check for any water leakage from the unit. Outdoor. Check for any HP or LP alarm. Check any abnormal noise or vibration in the compressor. Check any abnormal noise or vibration in the condenser. Cleanliness of the outdoor area. Now we will study top issues and how to troubleshoot them. Please take a moment to review the troubleshoot ideas. Use a scroll bar to view more. Now let's study about Precision Air Conditioning Unit (PAC). Most businesses today are reliant upon highly developed and sensitive electronic systems which require precise and stable environments. Information processing is the lifeblood of all critical operations. Therefore, reliability of equipment in the server room or data center is vital to the business processes. IT hardware produces an unusual concentrated heat load and at the same time is very sensitive to changes in temperature or humidity. A temperature and or humidity swing can produce problems ranging from processed gibberish to a complete system shutdown. This can create huge losses for the company depending on the length of the interruption and the value of time and data lost. Standard comfort air conditioning is not designed to handle the heat load concentration and heat load profile of technology rooms, nor is it designed to provide the precise temperature and humidity set point required for these applications. Precision air systems are designed for close temperature and humidity control. They provide high reliability for year-round operation with the ease of service, system flexibility, and redundancy necessary to keep the technology room up and running 24 hours a day. Let's understand more about PAC units. The Precision Air Conditioners, also known as CCU, that is Close Control Unit, or CRAC, that is Computer Room Air Conditioner, are refrigerating equipment specifically designed to provide precise control of temperature and humidity in all applications in which is required a very high degree of precision. The precision air conditioners are used in data centers where the refrigeration loads required can vary from 5 to 20 kilowatt. Server rooms, data centers, mobile, laboratories, and many other industrial applications. Let's learn about the objectives and applications of PAC. Precision air conditioners are designed specifically to meet following objectives to be achieved with a very high degree of reliability. Air temperature control plus or minus 1 degree centigrade. Air humidity control plus or minus 7 or 8%. High airflow rate. Year-round operation, 24 hours a day, 365 days a year without any interruption. Precision air conditioning finds application in places like the following that require a technological environment characterized by high levels of heat value to dissipate. Data processing centers, call centers, internet providers, server rooms, control rooms, museums, luxury hotels. You must be wondering, in addition to air conditioner, why we need a PAC. Let us discuss about it. Sensible heat ratio. In a technology room like a data center or server room, there are no people, the entry of outdoor air is minimal and almost the entire heating load is sensible, coming from lighting, IT equipment, etc. And there is no addition of humidity. The sensible heat ratio, that is ratio of sensible cooling to total cooling, therefore is very high, and a normal air conditioner cannot match this cooling profile. Therefore, we need a special system to cater for such load, and this is where the PACs come in, which are designed to meet this specific requirement of high sensible heat ratio. Temperature and humidity. The electronic components have little tolerance to varying temperature and humidity, and due to the varying load in such environments, the regular ACs are just not fast enough to maintain the parameters within the range acceptable. Precision air conditioners have the sophisticated, fast-acting, microprocessor-based controls necessary to react quickly to changing conditions and maintain the tight tolerances required for a stable environment. Precision air systems usually include multiple stages of cooling and heating, a humidifier, and a dedicated dehumidification cycle, allowing them to satisfy any and all temperature and humidity control requirements. Air quality. In addition to the temperature and humidity, the air quality with respect to dust and suspended particles also needs to be maintained in the critical rooms. For this, we need a very high CFM, that is flow of air through the unit, to not only ensure better distribution but also more air flowing through the higher efficiency filters in the unit. PACs are designed to meet this requirement as well, having a CFM to 600 to 800 as against that of 300 to 400 of conventional units. Continuous operation. The equipment in rooms critical to business runs almost through the year, and so is the expectation from the supporting infrastructure. PACs are designed for continuous operation, maintain the environment in all seasons, and redundancy is normally built in the design to ensure continuous availability of required functionality. Next, let us understand the working principle of PAC. Working principle of PAC is the same as any other AC, with the difference being in the components and control systems used for maintaining the air quality to a high degree of precision. The differences being higher nominal cooling capacity, higher sensible heat removal, greater accuracy or regulation of temperature and humidity, additional humidifier or dehumidifier, higher air volume and speed, multiple gas circuits, specialized heavy-duty components for continuous running, more complex solid-state controls. What are the components of PAC? Let's see. High-efficiency variable speed inverter scroll compressors may be used. Electrically commutated fans are used for higher efficiencies. Humidifier is added. PAC may have dehumidifying cycles. The plate area of heat exchanger is reduced to provide more latent cooling. Electronic expansion valves are used for better control. Microprocessor control systems to ensure optimal operation of components under all conditions. Now we will take a look at the classification of PAC. Please take a moment to review this classification. Now we will study in detail the PAC systems as per the condenser cooling mechanism. Air-cooled system configuration. Refrigeration system is split between indoor air conditioner and outdoor air-cooled heat rejection unit. Compressors can be located in the indoor or outdoor equipment. For security and maintenance, compressors are usually located in the indoor unit. Refrigerant pipelines, 2 per compressor, interconnect two halves of the system. Refrigerant piping design is critical. The design must address pressure losses, refrigerant velocities, oil return, and traps. Qualified expert contractors should install the service unit. Excellent for multiple units and expanding installations. Each system is a self-contained, standalone module. Water-cooled system configuration. Indoor air conditioner is a complete self-contained refrigeration system. Heat is rejected to a coolant water supply via a heat exchanger in the indoor unit. The coolant water is then usually pumped to a cooling tower and recirculated. Other water sources such as wells also can be used. Tower should be designed with redundancy or an emergency backup water supply should be available. Water treatment is required when a cooling tower is used. Underflow system recommended. Most computer hardware is designed to take air in at the front of the unit and let it out through the back of the unit. The precision air conditioner takes warm room air in at the top and delivers cool air through the floor, permitting higher air quantities without disturbing the occupants. Modern technology rooms used a raised floor with a minimum clearance height of 9 feet, preferably 12 to 18 feet, to serve as a cable raceway and act as an ideal air distribution plenum. Air conditioner CPU underfloor system floor. Overhead system recommended for small room applications only. Overhead systems discharge air into either a plenum or ductwork. These units are suited for areas where raised floors are less than 12 feet high. The precision air conditioner takes warm room air in through the front of the unit and delivers cool air through a plenum connected to the top of the unit and back down over the equipment. Considerable turbulence exists at upper air levels due to conflicting air streams from the IT equipment. The overhead system is not recommended in large room applications because the uneven distribution of cool air heightens as space increases, resulting in hot spots and cold spots. A further problem with overhead ducts is their inflexibility to meet changes in hardware location, resulting in hot spots and cold spots that are often impossible or extremely expensive to remedy. Now we will study maintenance protocol. Ensure drain is not closed. Clean package or split AC or body and surroundings for cleanliness. Check for any abnormal noise or vibration. Check unit status. Check supply air damper valve status to be open. Check set point. Should be as per requirement. Check for return air duct dampers to be open. Check evaporator coils should be clean and free from dirt. Check filter cleanliness. For abnormal noise and vibration in condenser unit, check drain tray for water clogging. Clean condenser coil with blower or water. Any leakage of gas if found short, then charge them. Suction and discharge pressure and record. Current of unit and record. Thermostat and remote operation. All electrical connection. Clean unit by cloth and blower. Now we will have a look at the maintenance protocol. Please take a moment to review maintenance protocol. Use scroll bar to view more. Now we will study top issues that you may face while using PAC and will study how to troubleshoot them. Please take a moment to review it. Use scroll bar to view more. Let's learn about another type of air cooling system called chilled beams. A chill beam is an air distribution device with an integral coil that may be installed within a space in order to provide sensible cooling and heating. A chill beam is a type of convection HVAC system designed to heat or cool large buildings. Pipes of water are passed through a beam, that is a heat exchanger, either integrated into standard suspended ceiling systems or suspended a short distance from the ceiling of a room. As the beam chills the air around it, the air becomes denser and falls to the floor. It is replaced by warmer air moving up from below, causing a constant flow of convection and cooling the room. There are two main types of chill beams, active and passive. Now we will have a look at passive chill beams. A passive chill beam is one that is not ducted, does not supply primary air, and does not utilize fan-powered equipment for any portion of the air that crosses the coil. They rely on induction air being drawn across the coil by the natural gravitational forces and buoyancy of air. Warm air rising to the ceiling enters the beam from above as the chilled air that has passed through the coil drops down. The motion of the cool air dropping creates a pressure drop behind it that draws more warm air through the coil. Let us understand the active chilled beams. Active chill beams are those that have ductwork attached to them, providing a specific amount of primary air to the pressurized plenum within the device to be discharged through induction nozzles, mix with entrained air and ventilate the room. The main air handling unit supplies primary air into the various rooms through the chilled beam. An active chilled beam uses the primary air supply to induce warm room air into the beam's cooling battery. In order to cool or heat the room, either cold or warm water is circulated through the beam's battery. Active chill beams are able to replica watches induce and condition 4 to 5 times as much room air as fresh air supplied. The recirculated air and the primary air are mixed prior to being reintroduced into the room by nozzles or slots along the beam. Active beams should be utilized when sensible cooling, heating and ventilation air are required. If the design calls for supplementary cooling only or the complete ventilation requirements of the building's design are being met by some other means, passive beams may be used. Classrooms, private and public office buildings, meeting facilities, healthcare facilities, other environments that may have moderate to high sensible heat ratios, and building retrofits where space for new mechanical equipment may be limited are all good applications for active chill beams. Passive chill beams are a good solution to provide sensible cooling in labs or other spaces where processes and people generate high heat loads, especially those that are sensitive to changes in pressure or ventilation and require no additional airflow. Some applications may have a ventilation rate requirement or high enough latent load that a traditional HVAC system would be more appropriate for use than active chill beams, but could benefit from the use of passive beams for supplementary cooling. Building retrofits where additional cooling is required but the original ventilation system will remain in place are also good passive beam applications. Let us understand the benefits of using chilled beams. Various methods of design exist, each possessing their own set of risk and reward. Chilled beam systems can provide several benefits including potential reductions in initial costs of equipment and construction material, increase in occupant comfort beyond that which is achievable through traditional systems, space adaptability, energy efficiency, simple operation and maintenance. An increase in overall comfort in a space conditioned with chill beams is mostly a result of the decrease in noise, draft conditions and temperature inconsistency. Now take a look at top issues and how to troubleshoot them. Use scroll bar to view more. Now we will have a look at cleaning instructions. The chill beam unit contains no moving or consumable parts. Therefore, the maintenance requirements are limited to periodic inspection for leakage and occasional cleaning of the heat exchanger coil and induction grill. The accumulation of dust on the heat exchanger coil can eventually restrict the airflow through the coil, reducing cooling and heating performance. The inspection frequency is subject to the environmental conditions and occupancy levels. For example, environments where bed linen is in use will require more frequent cleaning than office environments. It is recommended that the beams be inspected on an annual basis until a pattern is established. To clean the heat exchanger coil, if cleaning is necessary, follow appropriate steps to access the beam's coil located above the ceiling. Using a soft nozzle brush attached to vacuum cleaner, gently vacuum back and forth in the direction of the coil to remove any accumulated dust. Grills are provided by others. Follow the manufacturer's instructions to clean beam grills. This brings us to the last topic of this module, namely the thermal energy storage. Let us study this in greater detail. Thermal energy storage is like a battery for a building's air conditioning system. It uses standard cooling equipment plus an energy storage tank to shift all or a portion of a building's cooling needs to off-peak nighttime hours. During off-peak hours, chilled water or ice is stored inside energy storage tanks. The stored chilled water or ice is then used to cool the building occupants the next day. An extremely efficient system can be built by combining thermal storage with high-efficiency heat pumps. With conventional air conditioning systems that do not use thermal storage, equipment is shut down completely during the night and the heat pump is activated during the day to supply hot and cool air. On the other hand, with thermal storage air conditioning, heat pumps are activated during the night when energy demand is low to store thermal energy in thermal storage tanks. Chilled water and ice are stored in the tanks for cooling purposes, and hot water for either heating or hot water supply. During daytime of the next day when demand is high, thermal energy is drawn from the thermal storage tank for cooling, heating, or to supply hot water. The most appropriate type of thermal storage air conditioning system, such as water type or ice type system, can be selected depending on the scale and size of the installation space. In water thermal storage system underground, chilled water produced in the off-peak hours is stored in the thermal storage tank. In ice thermal storage system, ice is made in the thermal storage tank to store cold energy. The tank size can be kept smaller than with water thermal storage tanks. The thermal storage responds to peaks in cooling loads during the day by combining cold energy stored during the night with that produced during daytime. Consequently, the size of the installation capacity can be kept to almost half that of systems that do not utilize thermal storage. That brings us to the end of part 4 of this module on HVAC systems. In this module, you learned about types and working of fan coil units, types and maintenance of package units, working and types of VRF system, need of precision air conditioning, benefits of chill beams, thermal energy storage,